Welcome to this college algebra video on exponential functions. So I always like to start talking about exponential functions by introducing a little legend that I once heard of. And it's a legend about the person who invented the game of chess. And the legend goes that it was some kind of a peasant and he invented this game and the king heard about it. And the king said, wow, this is my favorite game. This is an awesome thing. I need to reward the person who invented it. So he offered the peasant whatever he would ask for, not being one that would go for the riches or gold or something like that. He just wanted to be able to feed his family, feed his village. And so he asked for 1 grain of rice for the first square of the chessboard. And he said, I'll come back tomorrow and you give me twice as much for the next square of the chessboard. And the next day, when I come back, give me twice as much for the next square of the chessboard. And just keep doing that until we run out of squares on the chessboard. Well, a chessboard is an 8 by 8 grid. So there are 64 squares on a chessboard. And so I want to do a little calculation and ask how much rice really was he asking for? And let's really try to get to the amount of rice he was asking for on that last square of the chessboard. So to be clear here, on the first day, he just wanted 1 grain of rice. Well, that's not going to feed too many people. But on the second day, he wants 2 grains of rice. And on the third day, not 3 grains of rice, but twice as much, so 4 grains of rice. And on the fourth day, twice as much again, so 8 grains of rice. Now we could try to just continue this pattern, doubling, but I'd really like to know, is there a quick way to jump to the 63rd square and the 64th square without having to figure out all of the number of grains of rice on all the squares in between? Well, here's a table that has extended that pattern out just a little bit farther, and I want to kind of focus in on the calculations that are necessary for this. Starting on the first square, it doesn't seem like we need any calculation. Of course, just 1 is equal to 1. But the next one, we doubled that amount from the first square, so 1 times 2. On the next square, we doubled that amount, so 1 times 2 times another 2. On the next square, it's 1 times 2 times 2 times 2 again, and so on. 1 times 2 times 2 times 2 times 2 again. And finally, 1 times 2 times 2 times 2 times 2 times 2 again. I'm kind of running out of room here. Now, I'm not going to be able to go very much farther writing these expressions this way. I'm going to run out of room here in this column. So is there a shorter way to write 1 times 2 times 2 times 2 times 2 times another 2? Well, sure there is. That's 1 times, and repeated multiplication, remember, can be written with an exponent. So these 4 factors of 2 multiplied times another 2 is actually the same as 2 to the 5th. And so we could really write each of these expressions as just a power of 2. This is 2 to the 5th, 2 to the 4th power, 2 to the 3rd, 2 to the 2nd power, 2 to the 1st power. Well, gee, could I write this one as a power of 2? If I just continue to follow this pattern, it would make sense that 1 is the same thing as 2 to the 0 power. So each calculation is really just a power of 2, but notice that the power of 2 is not lining up with the day that we're on. 2 to the 5th power is on the 6th day. 2 to the 4th power is on the 5th day. 2 to the 3rd power is on the 4th day. So it seems that the power of 2 is always 1 behind the day that we're on. So going back to our original question, if we want to find the number of grains of rice on the 63rd day and 64th day, the calculations we actually need to do are 2 to the 62nd power and 2 to the 63rd power. Now you can see those are fairly large numbers. Those are basically 19-digit numbers. So what do those numbers really mean? It's kind of hard to wrap our brains around such large numbers. I mean, grains of rice are pretty small. So are we talking about bags and bags of rice? Are we talking about a dump truck full of rice? Are we talking about a warehouse full of rice? Well, let's take a look. Now I'm going to start with an assumption that 1,000 grains of rice could fit into 1 cubic inch. That's kind of like the size of a sugar cube. So the volume of rice on the 64th square alone would be the number of grains of rice divided by 1,000, which gets us to 9.22 times 10 to the 15th cubic inches. Let's divide that into cubic feet. So divide by 12 to the third power, and we get 5.34 times 10 to the 12th power cubic feet. So that would certainly fill up many, many rooms. Is it a warehouse full? Is it more than that? So we're going to turn this into cubic yards. So think of a giant crate, 1.98 times 10 to the 11th crates. If we think of a giant warehouse full of crates, I don't know if that many crates could fit into even the most giant warehouse you could think of. There are 1,760 yards in a mile. If we divide by 1760 cubed, we are now turning this into cubic miles. And so the number of grains of rice is going to fill 36.3 cubic miles. Now, to get a number like that, you would need a cube that is 3.3 miles long on each side. Now, I've indicated on this map the campus of Colorado Mesa University in Grand Junction, Colorado, where I teach college algebra. And if we were to put a cube 3.3 miles long on each side on top of that campus, here's what it would look like. 3.3 miles long, 3.3 miles wide, and 3.3 miles tall. That is a lot of rice. So the point I'm trying to make here is that our intuition is not very good when it comes to a concept like exponential growth. That's why we need to trust the math that we're going to learn in this section. Here's the definition of an exponential function. Let b be a real number that is greater than 0 but not equal to 1. Then the function f of x equals b to the x is the exponential function with base b. This is the simplest kind of exponential function that we can have. I want to quickly compare linear functions and exponential functions. So a linear function could be a plus b times x. If we take the operation addition and step it up, it's now multiplication. We take the operation multiplication, b times x, and make it one step up, b to the x power. We've now moved from a linear function to an exponential function. On a linear function, the constant a, the number that's not multiplied times x, gives us the y-intercept of the function. Well, it turns out on an exponential function, the number a, the number that is not raised to the power x, also gives us the y-intercept of the function. Why would that be? Remember that the y-intercept is the value of the function when x is equal to 0. Well, if we multiply a times b to the 0 power, that's a times 1, or a. In a linear function, the constant b, the number that's multiplied times x, tells us the slope of that function. It can tell us how steep the function is and whether the function is going uphill or downhill as we move from left to right. Well, the constant b, the base of our exponential function, tells us some similar things. It's not exactly the slope, but it does indicate how quickly the function is going to rise or fall. The constant b in an exponential function is going to tell us something similar. It's not quite a slope. For now, we can remember that b in a linear function represents a common difference, but for exponentials, b actually represents a common ratio. It's a factor that appears over and over and over again. As I said, the base of an exponential function can tell us whether the graph of the function will increase or whether it will decrease. Here are the basic graphs we expect for an exponential function. This is when b, the base of the exponential function, is greater than 1. We see what we call exponential growth. When the base b is between 0 and 1, we see a different pattern, which we call exponential decay. instead of the function increasing, the function decreases. Some of the important features of these graphs are the horizontal asymptotes. There's a horizontal asymptote of this graph at y equals 0, or the x-axis. There is a horizontal asymptote of this graph at y equals 0, or the x-axis. Taking the basic function y equals b to the x, to get a vertical shift, we would add a constant at the end of the entire function. To get a vertical stretch, we could multiply the function times a constant. To get horizontal shifts or stretches, we're going to see something that looks a little more like this. We're actually adding or subtracting a number to the exponent itself, or we're multiplying the exponent itself times some constant. To illustrate what different bases and different constants can do to an exponential function, let's start with this basic y equals 2 to the x function. This is the same one that illustrated the grains of rice on the chessboard. If we increase the value of b, you'll see that this curve can bend upward. It becomes steeper and steeper. If we decrease the base back to 2 and closer to 1, we can actually bend this curve down. As we get closer and closer to 1, the curve actually becomes more and more like a straight line. At base equal to 1, that is just a straight line, because 1 to any power equals 1. Now, as we go below 1 to a base between 0 and 1, we're going to see, instead of exponential growth, now we have exponential decay, is what it's called. The value of the function decreases and decreases. But notice we still have this asymptote of the x-axis, because a base to any power is always a positive number. We're never getting any y values that are negative. The only way to get negative values from an exponential function is to actually subtract the number after the exponential part. And what we see is that the location of the horizontal asymptote is either higher than the x-axis or below the x-axis. If we change the a value, we're going to see the y-intercept is going to change. At an a value of 2, the y-intercept's at 2. At an a value of 3, the y-intercept is 3. At an a value of 4, the y-intercept is 4, and so on. Here's what transformations would look like inside the function as we referred to it before. This is adding or subtracting a constant to every x in the function. And notice that if I change the value of c in this case, we see a horizontal shift to the right or shift to the left. And if I change the value of a, we see a stretch and a squash, although it's kind of hard to distinguish a horizontal stretch and squash versus a vertical stretch or squash. It might be worth your time to experiment a little bit on Desmos or a graphing calculator with some exponential functions of your own. Let's switch gears a bit and talk about solving exponential equations. So we're going to talk in this section about just some very basic methods. In future sections, we will get a little more sophisticated. So an example of an exponential equation is like this: 5 to the x power equals 125. The variable is, of course, the exponent in an exponential function. So one way we could solve this is just by trying different powers of x. This is a guess and check method. We could try 5 to the first. Well, that's just 5. 5 to the second, that's just 25. But 5 to the third power is exactly 125. So x must equal 3. Here's a tougher question. 2/3 to the x power equals 81 over 16. Now, don't let these fractions scare you. Again, we're going to try guess and check. 2/3 to the first power, of course, is 2/3. 2/3 to the second power is 4 over 9. Square the 2, square the 3. 2/3 to the 3 power is 8 over 27. 2 to the third power over 3 to the third power. Well, 8 over 27 still isn't getting us the numbers we want. If we get to 2/3 to the fourth power, what we find is 16 over 81. Well, those are the right numbers. They're just not in the correct places. 16 should be in the denominator. the 81 should be in the numerator. I have to think back and remember what kind of powers can move things from a numerator to the denominator and denominator to the numerator. Well, I remember that's negative powers that do that. So I'm going to refine my guess and say 2/3 to the negative fourth power. And that is exactly the power we need to get 81 over 16. So x in this case has to equal -4. Let's now talk about what I call the equal base method. We're going to start with 9 to the x equals 19,683. We could try our guess and check method again. And what I notice is that 9 to the fourth power is too small, but 9 to the fifth power is far too big. 9 to the fourth power at least seems closer to 19,000 than 9 to the fifth power. So we might think that the answer is probably closer to 4 than to 5. The equal base method takes the base of the x and tries to write it as a power of a smaller number. So I'm going to take 9 and realize that I can write it as 3 squared. So 9 to the x is the same as 3 squared to the x. At the same time, I'm going to try to write 19,683 as a power of that smaller number. Maybe it's a power of 3. Maybe I won't skip over the correct answer when I try powers of 3. Well, it turns out 19,683 is 3 to the 9th power. So I now have 3 to the 2x power equals 3 to the 9th power. Well, the only way for these two expressions to be equal, if they have equal bases, then their powers must be equal. So 2x must be equal to 9, or x is equal to 9 over 2. Now, at first glance, we thought the answer should be closer to 4 than to 5, but it turns out the actual value of x is exactly halfway between 4 and 5. So again, our intuition about exponential functions is not very good. Here's another problem. 2 to the x equals 4 to the 2x plus 1. Well, guess and check is not a very good method here. I could try guessing all day long, and I might never find a power of x that's going to make the two sides of the equation equal. So instead, let's take this bigger base 4 and try to make it the power of a smaller number. 4 is the same as 2 to the second power. Now 2 to the second power to the 2x plus 1, let's think about what properties of powers we have to apply here. We're going to multiply the exponent 2 times the exponent 2x plus 1. That means distributing 2 times 2x and 2 times 1. Since we have equal bases, the only way for these two expressions to be equal is if their powers are equal. So x must be equal to 4x plus 2. Subtract 4x from both sides and we get -3x equals 2. Divide both sides by -3 and x equals 2 over -3, or -2/3. Again, that's not a power of x that I probably would have guessed if we were just doing guess and check from the start. Finally, we're going to talk about one very common use of exponential functions, and that is in calculating interest. In the past, you may have talked about simple interest. Those are not the formulas we're going to concentrate on here today. We're going to talk about compound interest. The difference between compound interest and simple interest is that simple interest is just calculated at the very end of a time that you've left money in an account. For compound interest, money is added into your account on a regular basis so that the amount in your account continues to grow over time. For instance, annual compound interest is represented by this formula. A of t, the amount in your account, is p times 1 plus r to the t power. Now, p represents principal, the original amount invested. The base of this exponential function is 1 plus the interest rate, written as a decimal. The exponent of the exponential function is the amount of time you leave the money in the account. Once per year, some interest is calculated and added into the account so that the next year, the interest is calculated on a slightly higher amount. And the next year, the interest is calculated on a slightly higher amount again. We could even compound things more than once a year, multiple times per year. To do this, we use a slightly different formula. The number of compoundings is represented by this number n. And notice that the time is multiplied times n. However, if you compound multiple times per year, you're not going to get the full year's interest each time you compound. So you take the rate and divide it by the number of times compounding. Now you might think that adding interest in multiple times per year, but dividing the interest rate by that same number of times per year might kind of balance out and be the same as compounding once per year. But we're going to see that it's actually quite different. Suppose we invest $2,500 at 12% interest for 20 years. We're going to find the balance if the interest is compounded, first of all, once per year. So we're going to use the formula A equals P times 1 plus R to the T. The principal, P, is $2,500. The rate is 12%. We're going to write that as a decimal. And the amount of time, 20 years. If we enter this into a calculator, we'll find that the amount after 20 years is $24,115.73. Let's see if it makes any difference to compound every 6 months or twice per year. As soon as we compound multiple times a year, we're going to have to switch to this other formula. Principal, P, is still 2,500. T is still 20. R is still 0.12. But now we're going to introduce this number n. So if we're compounding every 6 months, that would be twice per year. N is going to equal 2. When we do this calculation, we get $25,714.29. That's quite a bit different than what we got when we compounded once per year. Well, twice a year was great, but maybe we could compound every quarter. That would be 4 times per year. So keep the principal, interest, and time the same, but now make n equal to 4. 4 times 20 for the time, and dividing the interest rate by 4. This time we'll get $26,602.23. Maybe monthly would be better than quarterly. So let's see what would happen if we compound 12 times per year. Now we get $27,231.38. So I see a definite pattern here. The more times we compound per year, the higher our amount of money goes. So I think we may have discovered maybe a get-rich-quick scheme, or at least a get-rich in 20 years scheme. If we can just convince somebody to compound this money more and more times per year, what if we could get it up to infinite times per year? Maybe we could make infinite money. Well, let's see if that's true. If we compound 365 times a year, so daily, the n is 365, still the same principal, interest rate, and amount of time. Now our money is $27,547.07. If we can compound every hour, there are 8,760 hours in a year, then the amount of money we make is $27,557.49. Now, if we look at this summary again, we notice that the amount of change each time as we add more and more compounding, the amount of change is getting smaller and smaller. So the difference between 25,000 and 26,000 was much more than the difference between 27,547 and 27,557. In fact, if we go to compounding every minute, we only get up to 27,557.93. Rather than now try to compound every second, let's think about compounding infinitely many times per year. The word for this kind of compounding is called continuous compounding. And when we compound continuously, we actually change our formula. Now we're going to use this third formula. A is equal to P times e to the RT. And we'll talk a little bit about this constant here in just a second. If we put this into our calculator with 2,500 times e to the 0.12 times 20, we get an amount of $27,557.94. So it turns out that continuous compounding is the best that we can possibly do. Unfortunately, we can't make infinite money, but using the continuous compounding formula, we get the maximum possible return on our investment. Now, you might ask yourself, is a 12% interest rate compounded continuously really a realistic expectation? Well, not really, but there are definitely accounts that can give that much interest, not necessarily at a continuous compounding rate, but compounded daily. Unfortunately, those are not savings accounts. That's a typical interest rate and a typical kind of compounding found on credit cards. That's why it is so easy for credit card debt to pile up very quickly. When we're using the continuous compounding formula, we'll use a value of E stored on our calculator. This number E is kind of like the number pi in that it is an irrational number. It is a constant. It does not change. It's not a variable, but it is a number. Decimal expansion of E goes on forever, never repeating and never falling into any kind of a pattern. To understand where the number E comes from, we actually look at this function, the quantity 1 plus 1 over x to the x power, and look at values as x gets bigger and bigger and bigger. Here are some examples of larger and larger numbers plugged in to that function in place of x. Here are a few more examples of that function with even larger values of x. And you can see that the value is approaching a very specific number. That number is what we call the number E. On the calculator, it is 2.718281828, and that decimal continues forever without actually ever going into a pattern. It does look like it's starting to have a pattern, but there is no pattern in there. On a calculator, you can find that button either by hitting second and the division symbol, or if you want to take e to a power, hit second and the ln button. Hopefully you've learned a little bit about exponential functions and some of their uses in real life. Thank you for watching this video, and we'll see you next time.